Hey guys, in this video, we're going to go ahead and we're going to introduce something called the differential form of a line integral. So let's go ahead and let's maybe just quickly recall how we defined a line integral. So we said that we could integrate a function of both x and y over some curve C. And when we're performing a line integral, we're integrating with respect to s, where s is this little piece of arc length along our curve C. And on Tuesday, we went ahead and we showed that we could actually think of a line integral in a slightly different context. So we can actually write our line integral as the integral over a curve, but this time instead of thinking about having a surface that our curve is laying below and we're finding the area above our curve and below our surface, we can also think about our curve as traveling either through space or through the plane through a vector field. So we'll think about this as traveling through some vector field F. And now as our curve is traveling through the vector field, well, we're going to integrate with respect to our curve, which is given by some vector valued function r. So when I write C, I'm really representing C as the vector valued function r of t, and my function of x and y, or x, y, and z, if we have a function of three variables, just represents the vector field, right? So we can actually go ahead and we can actually take this a few steps further. So we can instead imagine our vector field as being given by some sort of a vector valued function that looks something like mi plus nj. And we can also rewrite this dr. We can rewrite this as dr dt times dt. I'll erase the dot there because I don't want us to confuse it with a dot product at that point, right? So now what we have our vector field, which is given by mi plus nj, and that's being multiplied by this dr dt, but that's just the derivative of our r of t, which came from our curve. So we could also think about this as now being the integral over our curve C of mi plus nj dotted with the derivative of r of t. Well, if we come back up here, we can think about r of t as being some x of t in the I direction plus some y of t in the j direction. So the derivative of r of t would look something like an x prime of t in the I direction plus some y prime of t in the j direction. So now if we go ahead and we actually compute this dot product, what we're left with is the integral over our curve C of m times x prime, which I can write as dx dt, plus n times y prime, which I can write as dy dt, and both of these are now being multiplied by dt. So we can clean this up a little bit, and we can write this as the integral over our curve C of m dx plus n dy. And this is what we're going to call the differential form of a line integral. So let's go ahead and let's see if we can actually evaluate a line integral in this differential form. So let's let C be a circle of radius 3. Given by the vector valued function r of t which is going to be 3 cosine of t in the I direction, plus 3 sine of t in the j direction. And here we'll look at values of t between 0 and 2 pi. Right. Now, we'll go ahead and we'll evaluate the line integral. Let's evaluate y dx plus 2x dy. All right, so this is kind of how we're thinking through, or this is where we're going to begin thinking through our integral. All right, so first thing that we want to consider is we want to think back to our curve. All right, so what does our curve give us? Well, it gives us the x-coordinates and the y-coordinates that we're going to be integrating over. So we really want to think about this right here as being our x of t, and I really want to think about this 3 sine of t as our y of t. Right? So I have my x values and I have my y values. Now those, I can actually go ahead and I can plug directly back into the integral that we're trying to evaluate. So my y values, I said, were 3 sine of t, so I have my 3 sine of t dx plus 2 times my x-coordinate, but my x-coordinates were 3 cosine of t. And that's being integrated with respect to y. Right. So this is where we have to think a little bit harder, right? We have this kind of strange integral form here, where we're trying to integrate 3 sine of t with respect to x and a 6 cosine of t with respect to y. The thing is x, y, and t are all somewhat intricately related, right? So it's not that x and t are independent, so we can't just evaluate, say, this integral here and write it as a 3x sine of t, or evaluate the other integral and write it as a 6y cosine of t, because there's this dependence between x and t, y and t, and since x and y are both dependent on t, x and y are both dependent on one another. So they're not these independent variables like we were looking at in chapter 14 when we were integrating with respect to when we were integrating in space. So what we have to do here is we have to find a way to replace that dx and dy with something that makes a little bit of sense. Well, it's actually easier than I think most of us want to make it out to seem. We're actually going to go back to our definition of x and our definition of y, and if we take our derivatives, or in particular find our differentials, we know that dx is just going to be -3 sine of t dt. So we're going to be able to replace the dx with a -3 sine of t dt. And something similar is going to happen with our y of t. So if we go ahead and we compute this derivative, we'll have a dy is going to be a 3 cosine of t dt. So now we can go ahead and we can substitute these back into our integral. And we still have the integral over a curve. 3 sine of t comes along for the ride, but we're replacing dx with a -3 sine of t dt. And we still have our +6 cosine of t, but now we're replacing our dy with a 3 cosine of t dt. So now what we really have is now we actually have an integral in terms of a single variable t. So notice we no longer have x's, we no longer have y's, we only have this variable t. So all of our functions are functions of t, and we are only integrating with respect to t. So really we've taken our line integral in this strange differential form and we've turned it into a normal Calc 1 integral. So let's go ahead and let's clean this up a little bit before we try to integrate. So we've got the integral over our curve, but remember, we've kind of incorporated the curve into the integral now. And now we're really just integrating with respect to t. And we know that we just want to look at the values of t between 0 and 2 pi. So we can replace our limits of integration with 0 and 2 pi. Our integrand is now going to be 3 times negative 3, so that sounds like a negative 9 sine squared of t. And to that, we're adding an 18 cosine squared of t. And we're integrating both of these now with respect to t. All right, so all things considered, we've now taken this from this strange line integral differential, the differential form of a line integral, and we're now trying to evaluate just a normal Calc 1 integral. So at this point, we're just going to go ahead and we're going to run through this pretty quickly. Basically, it's going to be a few power reducing formulas, and then we'll simplify, we'll plug in some stuff, and we'll end up with an answer. So let's see what happens as we go through this. So we'll have integral from 0 to 2 pi still. I want to use my power reducing formula on sine. So this is going to be a negative 9/2 times 1 minus cosine of 2t. I guess it would be all over 2, but I already brought the 2 out, so I don't need to divide by 2. Plus, we have an 18 over 2, so that's going to be a 9. And then we're going to have a 1 plus cosine of 2t. And that's being integrated with respect to t. So, kind of keep going. Just a little bit of algebra that we have to keep up with. So still integral from 0 to 2 pi. We'll have a negative 9/2 plus a 9/2 cosine of 2t plus a 9 plus 9 cosine of 2t. All right, so again, still just kind of keeping up with some algebra here. So what can we do? Well, integral 0 to 2 pi. What can we combine? Well, it looks like we have a negative 9/2 and a 9. So we could write that as 18/2 minus 9/2. That gives us a 9/2. And then we have a 9/2 cosine of 2t plus a 9 cosine of 2t. So that's going to give us a 27/2 cosine of 2t. Now we can go ahead and integrate. So we're left with a 9/2 t. And then it looks like we're going to be left with a 27/4 sine of 2t. And we're just going to take this from 0 up to 2 pi. So if we plug in a 2 pi, that's going to give us a 9 pi plus 27/4 times sine of 4 pi. Well, sine of 4 pi is 0. Minus, if we plug in 0, we're going to have 0. And then 27/4 times sine of 0, which is also 0. So what we're left with is just 9 pi. So the bulk of this problem is definitely the changing the differential form of our line integral into a form that we can integrate. And basically once we get there, it turns into a Calc 1 problem, and we just have to go through a few steps where maybe we simplify the integrand before we integrate. But once we're able to get to that point, it's a fairly straightforward problem. So with that, I think I'm going to go ahead and leave this video here. There will be another video on Canvas that I'd like you to watch, so go ahead and watch that one before Friday's lesson as well. Thank you.